This video is in place of anyone who is not able to make it to the Google Hangout on March 30th. Hi, welcome back from spring break. I'd like to just talk with you about a few announcements that happened recently. So right as we went on break, College Board put out an announcement about how AP tests would be changed or modified this year, given the circumstances. And so if you look basically on our Schoology page, or if you just did an internet search for AP exam changes March 20th, you would find out that our exam is going to be an online exam. Even if we're back in school, by the time of the exam, it will still be this format because it's just too hard to develop two different exams at the same time. So it will be an online exam. There will be 2 dates. I know that I was just sent a survey this weekend asking me my opinions about dates and such, so I think those are still a little bit in flux. We are expecting another announcement from College Board on April 3rd, and so I think at that point we'll probably know what the 2 dates are, but you get to pick one of the dates. They did say in something that I read that one of the dates is going to be in May, and then one will be later. I don't know if that means later in May or an actual date in June. I think that is to accommodate schools and, especially those that start after Labor Day that might be having a harder time covering the content that is on the test, just to make sure that they have a fair shot at earning their college credit. The exam itself is only going to be 45 minutes long, and it's not going to have any multiple choice. And both of those are actually to make it harder for people to cheat. So if you think about it, even as taking an exam at home, you clearly are going to be able to make use of certain things like notes, right? You are at home, you are taking this test by yourself, potentially. And the thing is, if you only have 45 minutes, you really don't have time to be looking up a lot of things. So if you've ever taken such a test before that has it's a very open note, but a short time frame, the notes actually kind of slow you down. And so I would encourage you to not think of it as an open note test, even though it is. Just prepare for it as if it were a normal AP test, in the sense of not thinking of having other resources available to you. And then the fact that you do, well, bonus, you can quick look up something if you need to, but if you're doing that for a lot of things, there's no way you're going to finish in the time that they're allotting. The fact that it will be a free response sort of situation, I don't think we should necessarily think, oh, 45 minutes, that sounds like 3 free response questions. I do not think that is how it's going to be. I think it will be much more like short answer, or maybe like free response questions with pieces that are linked, but not necessarily like 3 or 4 like we typically see, maybe more like 6 linked together with one question stem, but trying to cross a lot of different topics within use of that one stem. Now, obviously, this is all me just guessing. I don't know anything for sure, which is stressful, I understand, and I feel badly for that. Because usually Mr. Covey and I could give you a lot of information about what to expect on the test, and this year we just really can't. So I think the best preparation is for you to know your math as best as you can. I would encourage you to still take the test. I do think that is the game that we signed up to play. So I think it would be in your best interest to still try to get that college credit. And I did put in a question on that survey that I received asking about the opportunity for BC students to maybe sign up to take both the AB and the BC test, since there will be multiple dates. The BC test doesn't have enough questions on it as it stands for them to develop an AB subscore for you. And I always felt that that was one of the great things about our exam, is that you pay 1 exam fee and you get 2 scores. And I've had students in BC in the past who've gotten, credit for Calc 1 or credit for Calc 2 or credit for both. And it would be really nice for you all to have that opportunity. So I did ask them to consider allowing BC students to also take the AB exam. If they're both only 45 minutes, that's still less time than you would have spent taking a 3-hour and 15-minute exam had things gone according to plan. Okay? Another thing I wanted to point out was that there are these lovely YouTube videos that are being developed by 4 superstar calculus teachers. These are all people who I have seen at the one time I got to go to the reading. They are bigwigs in AP calculus circles. So 2 of them are working on the AB videos, and then 2 of them are working on the BC videos. There's a YouTube channel that has videos actually for a majority of AP classes. So if you haven't heard about them from other teachers, you might want to take a look and see if you can find your AP US history or whatever else you might be taking. There's probably some videos out there for other classes that you're in as well that are AP courses. For BC, the first several videos are all going to be finishing out content from this year. So there are schools that haven't finished everything topics-wise, and they want to make sure that they are giving access to that content to everyone. So especially schools that maybe their teachers don't have the capability of making videos like this one that I'm doing right now. If there's schools like that, hopefully by having these videos on YouTube, those schools or those students then would have more access to the content. So the first few videos are maybe not going to be as useful for us per se, because we have actually done those topics. So they're talking about parametrics in these first few videos, and then they're going to shift gears this week to do some videos about series, but we just finished that. So feel free to definitely watch them, like if you're looking for something to do, or not just like if you're looking for something to do and you want it to be more meaningful than like watching more Netflix or whatever, then that would be a good use of your time. There are materials that go with each video, and so those links are posted on our Schoology page, so you can take a look at that. You also can just go to YouTube and search for it. It's not that hard to find. They are live, and so it's 8 in the morning for the BC ones, and the AB ones are at something like 2 in the afternoon, question mark. So you can watch it live. The time I watched it live, I found it frustrating because there are times when the teacher would just be like, hey, work on this problem. And then like he sets a timer for 3 minutes. Okay, so I don't know why I would be watching it live if I just wanted to like hang out for 3 minutes. I would rather watch it personally. I'd rather watch it after the fact and be able to do the fast forward rewind thing as much as I feel like it. So that's my own thought. But there are handouts, like I said, so if you wanted to like look at the handouts and be like, hey, what problems is he doing in this video? You could look at the problems ahead and then be like, okay, that looks like stuff I already know, I'm not going to bother, or that looks like stuff that I could use reviewing, and watch it. Okay. Once they get into full-time AP review mode, Mr. Covey and I certainly have the thought that we might assign some of those to you as part of your online learning if we're still not in school. Okay. So sorry, that was a very long, like rambling thing. I've been alone with my dog far too long. I need someone human to talk to. So we are now 8 minutes in, and I'm going to now shift gears and talk about some polar area. So if you were able to pick up the packet before we moved to school at home, you might have a packet on white paper, and I am looking right now at page 33. So you might wonder, why are we looking at page 33? What happened to all the stuff that was ahead of page 33? Well, with the change from College Board, they said that no longer will error bounds be part of the AP test this year, and Mr. Covey and I debated that for quite a long time and have come to peace with the idea that we're not going to do error bounds with you. We think you can pick that up in a real analysis class if you are in that later on. I know that's actually the class in which I encountered this idea. So I don't think that you'll have a hard time not knowing it from your calculus class, is my point. So given that, we are going to probably skip a lot of the beginning of this packet, maybe come back and do some of the Taylor review worksheets. Maybe not, we'll have to see, haven't planned that much. But that's why we're on page 33. Okay, so I'd like you to pause the video now, and I'd like you to try these 2 problems. So the first one says find when r equals 0. And so the when means find the value of theta. And the second problem is the integral of cosine squared. And for that one, you do need to think about identities, like trig identities. Okay, so do the best you can. I'm going to pause. You're going to pause. You're going to work, and then you're going to come back. Okay, so here's my work for problem number 1. So please remember that the reason that you would want to solve a polar equation when r equals 0 is because r equals 0 means that you're at the pole. At the pole means r equals 0. So that is the situation in which you would be doing something like this. And from that juncture on, like my work in orange there is just, some algebra. And then remember that when I'm looking for these angles, I'm going to go around the unit circle twice, and then this will give me my two solutions, okay? So I would have 7 pi over 12 plus multiples of pi, and 11 pi over 12 plus multiples of pi, okay? And so that n can be any natural number, and then the 6 switches to a 12 because you divide it through by 2. Okay, so I'm going to scroll back up on this for a second in case you need to take a look at it. Feel free to pause your own video. Okay, and then we'll take a look at question number 2. So over to the side, I have a list of trig identities. And so in your notes packet on page 33, there is some space where it says trig identities to remember. If you didn't get this packet, by the way, there's a PDF of it on Schoology in today's folder, but it's not a big deal. Like if you don't have this particular piece of paper, you're going to be able to just make your own notes. It'll be okay. All right, so these trig identities, the first one clearly is our Pythagorean identity. Okay, and then these next two are double angle identities. And you might remember from math analysis that the double angle for cosine has a variety of different versions. The one that I personally have memorized is the one that is right here on your piece of paper, because I feel like it's easy to memorize. It's just like the Pythagorean identity except subtraction. So if, cosine squared plus sine squared equals 1, this is cosine squared minus sine squared. So that's not too bad to remember. And then from that, you can derive the other versions. So for instance, if I were to replace the sine squared with 1 minus cosine squared, that's all that happened right here, and then combine like terms, I would get that cosine of 2x is this. And then if you isolate there for cosine squared, you get this identity. And then if you had done a similar idea, but kept the sine squared and instead replaced the cosine squared, right, with like 1 minus sine squared, and then solve for the sine squared, you'd get this version. So I don't have, secret, I don't have any of these down here full on memorized. I mean, like halfway memorized. Maybe, right? Is kind of where my thinking is, because I know I can always rederive, and I am very bad about remembering positives and negatives. And if you take a look at those last two lines, the only thing that's different is this plus or this minus. Like that is something that I am going to screw up if I don't just think it through. Okay, now if you're a good memorizer, good, go with your strength, right? So if you're a good memorizer, go ahead and memorize. But the thing that we're going to make use of here is this guy. Okay, and so you might say, well, why didn't we just do a U substitution? Why didn't we? Well, because if U were cosine of x, then we would need a sine of x over here. Like we don't have that. There's no way to get that. That's not an insert and balance kind of situation. But by doing this substitution, not a U substitution, but a trig identity substitution, then I can just split this up into two nice little pieces. And then think of each of those as a separate little integral with a tiny little baby U substitution involved, right? My tiny little baby U substitution is going to have me put in a 2 because this 2x is my U, and then balance that with a 1/2, and everything is all legit. Okay, so hopefully that's what you got. That's just a little review question. We did that back, in our, I don't know, in our integration unit, maybe, something like that. Okay. This little slide here is a reminder of the key things about polar. So in polar coordinates, we think about x as being r cosine theta and y as being r sine theta. And if you think of this picture, you know that this has to be true, right? X squared plus y squared is r squared. Tangent of this angle is opposite over adjacent, just like always. One thing that is a little confusing about polar graphing is when r is negative. So there's some place that's called the pole, and that's also the origin. And then you're measuring your angles from this ray. And so my positive thetas go this way. My negative thetas would go the other way. And then a positive R value would be marching out from the pole along that end of where the rotation is. But if I had, like, let's say I had pi/6 as my angle. If I had -2 as my R value, that would mean I rotate to pi/6. But instead of going out 1, 2 units this way, I go 1, 2 units backwards. Okay, so that's just a little bit like getting your bearings with polar again. If at your house you still have your polar packet from the fall, I think it was on ivory colored paper like off-white, the first page of that has a very nice summary sheet about polar. I'll try to remember to post that again. Or if you guys, can you see first semester stuff? I think you can if you look in your archive classes. So in the polar folder from fall, there, I'm sure on Schoology there is that nice summary page. Okay, I need to step up the pace. We're going to be here all day. All right, so number 1 says to graph that. Now, FYI, I have never seen an example of a question off of the AP exam where you had to actually come up with the graph. But if you did need to, you just make a chart and you take different values of theta and find the r's that go with them and plot the dots, okay? So you go to whatever rotational angle, and then, like I said, positive r's go forward, negative r's go backward. But in reality, we're going to put this on our calculator and take a look, not really use polar graphing paper like this old school picture here. Okay, so in doing that, you should get a circle. The circle has a radius of 2. Okay, so the circle has a radius of 2 and its center is at 2, 0 in terms of rectangular coordinates, like right here. Okay, 2 units out across that horizontal axis. So if I have a circle with radius of 2, I know from geometry that area of a circle is pi times radius squared. And so this circle has an area of 4 pi. That's not too hard. Okay, now what we're moving to in what we're studying this week is what's called polar area. So we want to find the area bounded by different polar curves. Well, this polar curve is easy to figure out because it's a circle. So now let's think about what we used to do to find area in general, right? So if we have an XY coordinate plane, we then took whatever shape we had and we chopped it up into rectangles. So if we look here, this is the graph we were just looking at, the circle. And if I had rectangles to fit in, such as this one rectangle I've already drawn, okay, I could find the area of this semicircle, right, using those rectangles. And I would need to know an equation for that curve. So the Cartesian equation for a circle centered at 2, 0 would start out like that. And then the radius was 2. 2 squared is 4. So I'm thinking about the fact that this is the equation of a circle, right? You would have like x minus h squared plus y minus k squared equals r squared. Geometry fact, okay? So there's my Cartesian understanding of the circle. And if I isolated for y, I'd have a positive radical and a negative radical, like this. The positive radical would be this part, and the negative radical would be this part underneath. And so if I were to just find the area with rectangles in the top part, I then could double it and I'd have the area of the circle. So I could just say, all right, my area is going to be double. What would my bounds be? Yeah, 0 to 4. And then my equation is just the positive square root. Okay, so I could certainly throw that onto my calculator. That's great. But it's not always going to be a circle, right? There certainly are polar curves that are all loopy and stuff, and it's not going to be easy to just say, hey, let's just find a Cartesian equation for that shape. Like that happened to work in this case. So let's think about what our polar shape should be. So mathematicians try not to invent full-on new ideas. They try to tweak old ideas, right, to try to make them work. So if you think about polar, back here we had a picture of some polar graph paper. And so we want to be thinking about things in terms of rotating around, right? So as I move around, there's kind of like this rotation or this sweep of the angle theta. And that's what I started thinking about with this. I thought, okay, we should be thinking about, here's maybe where my first angle is, and then theta gets bigger. And so it's not chopped up into rectangles. It's chopped up into like little wedgy things, or like little, almost like sectors, right? So that's the shape that we're going to make use of. And you might think, well, have I ever done anything like this before? Because again, mathematicians don't like to make the new thing, okay? Well, you have done something like this before. You've done something like this in geometry, right? And it was called finding the area of a sector. So back in geometry, you said, all right, to find the area of a sector, and that was like you had a circle and you wanted to find the area of like this kind of space. You said, okay, I'm going to find the central angles measure and call that theta. And so theta out of 360 represents the fraction of the circle I'm talking about, and that fraction of the area, pi r squared. Now, if you think of that same formula, but now you say, well, I'm in calculus now, my friend, and we are not physics people. We are going to measure our angles in radians like people do. So then theta out of 2 pi would be the fraction that represents the fraction of the circle. So this fraction times pi r squared, the pi's would cancel, and then that leads to this beautiful guy in the navy blue down here. So area is 1/2 r squared times theta. And theta would then represent, like, would be these different angles. Like theta is changing as we sweep through our space and fill it up, okay? Much like with the rectangles, right? We want to sweep through this space and have like different locations of that width, so to speak. Okay, so we want to add up all of these different little pieces. What does that sound like to you when you want to add up a bunch of little things? Gosh, I really hope it sounds like a limit of a series. I hope it sounds like an integral to you. That would be fantastic. It should. Okay. So, oops, I think I missed talking about something. Okay, so that's going to be what we end up doing. All right, is we're going to add up a bunch of wedges. Okay, so on this slide, we're thinking about our circle still, just as a, for instance, we're going to do 1/2 r squared. We have d theta to represent, we're going to be taking a little change in theta. Those are all of our little slices. And then here is my addition and my bounds, right? So I'm adding up all of those slices, my angle going from 0 to 2 pi, okay? We know that r is this equation, so just substitute that in. And now I hope you see why we did the warm-up that we did, because we're going to end up with a cosine squared. So if we were doing this by hand, which chances are maybe not, but I believe in showing you all the things. So we would use our identity here in order to be able to integrate by hand. Now, when you get to the end of this, you do get 8 pi. And that's weird because we already know the answer, right? We know the answer from geometry. The answer should be 4 pi. We got 8 pi. So you might be like, hey, what's going on? Take 30 seconds. What is going on? Take a minute and think about it. All right, so I hope that you decided to look at your calculator. Okay, hopefully you put your calculator in polar mode and watched what happens as this graphs. And if you use the ball and chain setting, your graph is going to start here and it's going to go around and then it's going to come back around. And if you have set your window to go from 0 to 2 pi as these bounds are indicating, you'll see that you actually trace the circle a second time. So is that why we got 8 pi? You bet your sweet patootie that's why. So we need to make sure our bounds are set so that they actually are describing the shape. So what we've needed to do is to say, hey, we want to solve when r is equal to 0. We want to see what happens, like how does it come back to the beginning again? And so our bounds should actually be different than what we first said. If we solve this, we see cosine of theta equals 0. When is cosine equal to 0? At pi over 2 and at 3 pi over 2. Okay, so those are the bounds that we should have been using here and here. Okay, that was drawn really badly, but you know what I'm saying. Okay, put in pi over 2 as the lower bound and 3 pi over 2 as the upper bound, and you'll be all set. Okay, that was the mistake. All right, and I made that mistake intentionally because that is the mistake that students sometimes make. Okay, so think about your bounds. You're not going to necessarily be like just stuck in polar mode to do polar questions. Remember, there are times you want to be in function mode, but you do want to look at the graph in polar mode to get a sense of what's happening. Okay, so this question I'd like you to try mostly on your own, and then I'll come back and help you. So it says to graph this, you can graph it just using your calculator. You get this little cardioid. It's kind of like a little dented on the left, so it's not exactly a circle, it's a cardioid. And part B says, what is the area bounded from 0 to pi? Well, 0 to pi, as you will see on your calculator, corresponds to the top half of this shape. So that's the 0 to pi part. And so I'd like you to set that up and either use your calculator or by hand anti-differentiate and see what you get. And then the next question asks about 0 to 2 pi. And I would encourage you to think about symmetry. Okay, so pause the video and come back when you've tried those. Okay, so here is my solution. I did not use my calculator on this, like I showed the anti-differentiation by hand, but feel free to have like thrown this on your calculator. You would throw the integral on your calculator just in regular function mode, right? You'd have this part here as your y1. So y1 equals 2 plus cosine of x, and then you would just integrate. You'd have an x instead of a theta, but tomato, tomato, right, in terms of the calculator's thinking. And you should come out with 9 pi over 4. Now, the question down here is, well, how about from 0 to 2 pi? Well, confirming it on your calculator, 0 to 2 pi is the top half plus the bottom half of the cardioid. And so you can just make use of symmetry there by doubling it. Now, you might want to be a little cautious because there isn't left and right symmetry, right? Like if I'd known this part, I couldn't just double it and say, okay, well, that's the other side as well, right? So make sure that when you're quote unquote using symmetry, you actually have symmetry. All right, so this slide is just to show you the directions for this week, but again, these are on Schoology. Today, you should be watching the video of the 5 most common errors that were from the series test that you took online before spring break. You can skip around on that as much as you need. You should be able to go back into that assessment and see your own results at this point. So maybe do that first, see which ones you got wrong, and then go to the video and see if you can sort that out. By the end of the day on Wednesday, you should watch all of the polar videos. So this video is in place of the Hangout that that your teacher held on Monday, but you could watch this instead, that's fine. And then there is a book assignment on polar that we'd like you to work on over the next few days. So that should be done by the end of the day on Wednesday. You should have watched the videos for polar and done the polar problems. And that there's nothing else coming your way for the block day this week. Okay, so the video of the 5 most common errors, this video, the other videos that are listed as polar videos, the bookwork for polar. That's it from today to the end of Wednesday. Whichever day your class would meet typically. So for my classes, that's 6th period on Tuesday and 5th period on Wednesday. And for Mr. Covey's classes, those are both on Tuesday. Make sure you fill in the Google form from Schoology, whichever day you're supposed to have class, because attendance will be taken off of that Google form. Thanks so much, and I wish you all well. Miss you a lot.